So, hey guys, so I'm Manish. I'm one of the core protocol devs here at the MOI Protocol. We are a new layer 1 protocol that is kind of revolutionizing the blockchain space. And I just want to give you guys an introduction to how we're doing that today and kind of give you guys some insight into how to develop on MOI, what kind of applications and use cases that we're kind of opening up with this protocol, right? So, a simple definition of what MOI is it is a context-aware peer-to-peer protocol that enables the fabric of the stateful internet, right? The way we define the future for the blockchain space is that we are working towards what we call the stateful internet, an internet where participants are interacting with each other, creating value for each other, and persisting state in a private, safe, and shareable manner, like in the way that they intend to work. And at the fundamental, like the most simple analogy I can give you for the MOI protocol is that we're trying to take the real world and then make that happen in a digital way, right? Real interactions, real value transfers. In the way that the real world has constraints on them, the same constraints apply on the protocol. And the same things that the real world allows, this protocol allows us to do, right? And these are kind of like the three primary, I guess, enablements of this protocol, right? And the first one is an infinite scale network. We are not constrained by the Byzantine communication problems or the, what's the word for it? Forgot the exact word for it, but take a chain like Polygon or even Ethereum or Bitcoin for that matter, right? They have a certain node limit to how big they can get. And this is just because the amount of quadratic communication going on between them is honestly quite insane, right? It's just because everyone needs to be involved for every consensus, right? We have an infinite scale network that can scale up to millions, billions of nodes in reality. And it's a network that gets faster and more performant as the more nodes join the network, right? And as part of this infinite scale network, to really leverage the size of this network, you also have to have hyper-parallel consensus. Consensus does not require everyone in the network to participate in it. And yet you can have the same degree of security, right? In the same way that me transferring a real $50 note to someone is as valid as me doing it in front of 100 people, or if I do it in a private room, that transfer is real. It is constrained by the laws of physics, right? The note actually moved from my pocket to his. You cannot lie about that, right? This protocol kind of allows us to do that too, and I'll kind of break down how that happens. And the last one is light speed finality, right? All transactions in the network take sub 2 seconds, instant finality. No eventual finality, you don't have to wait 7 blocks for confirmations, nothing. To sub 2 second instant finality, and that 2 second mark is actually the worst it will ever be. And we'll probably only be making it better as we go. Right? And all of this, these three functions I just talked about, are enabled by the architecture of what we call participant centricity. The idea that the same way you have smart contracts in Ethereum, in MOI we have 3 primary primitives of objects, and they're called assets, logics, and files. And these primitives that participants interact with, they aren't independent objects in the network, but rather they are always owned or managed or controlled by a participant in the network, right? Just like in the real world. Money doesn't exist on its own, it exists as it belongs to somebody. And files don't just exist. Someone owns that file, someone wrote that file. There's history, characteristics, and behavior to these objects, and this protocol helps us index that and maintain that information. And doing so allows us to kind of manage them concurrently, right? Assets don't need to be you don't have to go through a central register or a registry to manage these assets moving between participants. These assets have native capabilities, and the protocol natively understands all assets. And this allows us to kind of transfer them in a purely peer-to-peer fashion. And I'll kind of illustrate that in the next slide. But the fact that they're participant-owned, like I was just saying, this opens up a degree of personalization and scalability that has never been seen before, right? And let's kind of break down an example of this, right? You can look at the Bitcoin account model, if you will. It's technically a UTXO, but then let's just, for the sake of this conversation and analogy, think of it as an account. There's just some Bitcoin balance associated with this address, right? And when we moved to Ethereum, we found a way to kind of manage, we really wanted to make sure that we had an internet of assets and we had the ability to kind of manage that across smart contracts, right? So you can see in the Ethereum address here, OX Ganesh, that he has an Ethereum balance that is natively understood by the protocol, but any balance he has as USDT or any other token for that matter needs to be indexed against him on the contract. right? And if someone wanted to move this asset, they would have to have the availability of the USDT contract to have the contract move. And we just saw an example from the seller team where they had to subtract balance and add the balance on the contract registry, right? And if I had to manage approvals or any other kind of staking or lockup-based logic, I would have to, again, depend on the DAI contract where I would have to maintain a registry or entry of these approvals all at the registry level, right? I don't maintain these at the participant level. And which means every participant trying to move that asset has to go through that contract and needs the availability of this contract to work, right? It's not possible for, let's say, me and Abhishek to make a transfer at the same time that Peter and AJ are making a transfer. It's not possible, and one of us would have to perform first. One of these transactions has to go first, right? In MOI, because everything is indexed on the participant side, right? The first big change is that all assets are native, right? Any asset you would create are natively understood by the account model. There is no native MOI. MOI is as native as any other token that a user would create. The only difference is that the MOI token is used for governance and staking and other functionality, but it's just as possible for DAOs to use those same native tokens that they would create just as natively as the MOI token, right? So the fact that multiple asset balances are all maintained in the participant, that's the first big step. So if I were to transfer this MUSD token, let's say, I would not need to go through the MUSD contract. And there may not even there's no necessity for an MUSD contract to exist, right? The token is a native cryptocurrency that are available in your wallet, and you can just as easily transfer it as you would transfer the MOI token, basically peer-to-peer fashion, right? And approvals, this is another part of the balance of the user that we can store, and the approvals they work exactly like your ERC20 approvals, but they're maintained at the participant side, right? This allows us all you have to lock are the two participants, right? In this approval case, I would need to lock the MOI participant and the spender who's Rahul. I only need their state lock, right? And lockups, excuse me a second. So lockups, this opens up a pretty interesting use case for MOI. How many of you have staked on Ethereum or held your money inside a contract before? Right? You have, right? So let's take the Ethereum staking contract, right? Every single person is taking about 32 ETH on that contract. And there's probably a few 100,000 ETH or more, actually, I'm not exactly sure of the number, but a lot of Ethereum on that one contract. Obviously, there's been no hack or exploit on that contract yet, but what if someone finds something, right? There's billions of dollars worth of, total locked up value from the community in that contract. And it's a big honeypot, and you've probably heard of this phrase, right? It's honeypot contracts. And how do we kind of mitigate that in MOI is that in India, we have this idea called fixed deposits. And I'm not sure if that's a concept available here in the States as well, but sorry? Term deposits. Okay, I guess that's the analogous version of it here. But the idea is that if I wanted a credit card in India, sometimes the bank would request me to put an FD and just secure a certain amount of money in your own wallet, in your own account, in your own bank account. And this would give me security that you cannot move that money. I know the money exists. It's in my issuing bank, so I can issue a credit card now. I can give you a good credit limit. So the same model here with MOI is that instead of the contract holding the value, the contract just makes an entry in just data. It's a registry saying, this is the amount of Ethereum I'm locking up, but that money is locked up back into the participant's wallet. And this way, there is no honeypot contract. If I broke the contract somehow, all I would know is who has what and who's locked up how much. The actual asset still sitting with the participant. And basically, if I wanted to exploit the whole contract, like all the staked Ethereum in the network, I would have to break every single staker's wallet, which is, let's just say, probabilistically not going to be happening, right? So this is one of the ways that MOI kind of prevents the participant-centric model of computation and execution kind of helps us avoid honeypots and security vulnerabilities that existing networks kind of have, right? And the same participant-centric architecture also has benefits in terms of how we execute logics, right? The first one, and this is the kind of one of the biggest novel things we did at MOI, is the idea of ephemeral states, right? We actually heard the phrase used, persistent state, and I guess the idea is that state can have expiry and stuff, right? But in MOI, ephemeral states means instead of the contract having to hold state, the participant can hold state. Imagine instead of holding a guardian contract, in MOI, by the way, validators are called guardians, and instead of having a huge guardian registry of address to the guardian data, which contains information about their node infrastructure, KYC, whatever, all that information is there. Instead of storing that in a central contract, I'm rather holding that at a participant level. And this way, all the other logics can also read that information, but this logic can manipulate that information when the participant actually is interacting with that logic, right? When that participant is not talking to that logic cannot manipulate that state without that participant actually being part of the transaction. He must be part of the assigned participant on that transaction, right? So you can see that in the first object I have here, that this is the current traditional smart contract model we have, which is there's a participant and there's a contract with some state inside it. But if I remove the state away from the contract and move that to the participant, and MOI actually supports all kinds of variations, like this whole matrix of possibilities here. But if I built a purely ephemeral logic, so the logic has no internal state, but all state is stored outside of it on its participants. Now, hundreds of people can speak to the same contract at the same time without waiting for contract availability, because the context is only changing on the participant side. So you can see in the second object here, there are two participants concurrently talking to the same contract, and they're stateful contracts. The state just happens to be on the participant side, right? You've opened up a whole use case for concurrency and performance here. And the last one, and this is called interactable calls, is the ability to bring in more than one participant. You can, I think as of the current spec, we can bring in as many as 6 people into the same call, and all of their ephemeral states become available to that logic. What's also beautiful about this is that thousands of these same interactable calls can happen concurrently at the same time, right? And you're just opening up a whole new kind of dimension to what kind of scaling and concurrency we can achieve on blockchain technology now, right? And hopefully, at this point, I'd just like to kind of stop anyone and ask questions if anyone has anything. Okay, I'll move on. So all of this, these participant-centric architecture, this new protocol, all of this is enabled by these 4 fundamental ideas, right? The 4 engineering pillars that we had to kind of make real before these things became possible. The first one is a new data structure. We call it the multi-link DAG. We're not really a blockchain, we're really what a multi-link DAG is, and I'll kind of show you what that looks like in a second. Second is a consensus that works on this new data structure, right? You need a consensus that understands the concept of a participant, their behaviors, their intrinsic context for that specific interaction, and how do you achieve consensus on that, right? We talked about how do you achieve consensus, how do you make sure that the participants in the second block, how do you make sure that they are safe, how do you make sure there's no double spend there, right? Buffer context takes care of all of that. Make sure that the participant is an understood paradigm in the consensus model. The piece of virtual machine runtime is our own virtual machine runtime. This is just actually one of the possible virtual machine runtimes that MOI supports. MOI intrinsically supports modularity in its virtual machine runtime. Developers can actually build on top of multiple virtual machines. Today, we do not have EVM compatibility, but who knows, down the line, the community could choose that it's important for them and build a second virtual machine that the chain supports. And we could add as many as you want. And making all this possible, right? You could not, today we tried to actually, and we didn't want to build a language, but we chose to do so because no programming language today can describe this concept of a participant, ephemeral states, native assets. All of these things are not something that you could do without writing a DSL, in which it just kind of meddles up auditability, readability, in my opinion. So we ended up writing a new language that kind of makes sure all of these features come through, right? So this is what the multi-link DAG kind of looks like, right? I'll kind of break it down for you guys a little by little, but in a nutshell, basically, every participant on the MOI protocol has their own chain state, right? And when there is a genesis chain off of which every account forks, and this is like the kind of spine of the network, right? This is the one contract. Every time a new person is born, it goes through the genesis contract. But every time a new participant is created, from henceforth, no one needs Genesis contract. So when Alice and Bob have a transaction, you only need to lock Alice's chain state and Bob's chain. And once you have their lock, you can do any kind of transaction between them. You don't need anybody else in the network to be involved in their transaction, right? And if Alice, Bob, and Carlos had to do something together, you can lock all 3 of them up for that particular transaction, right? You only lock up the people who need to be locked up for that particular transaction. This allows everybody else to continue to work on their own transactions without waiting for Alice and Bob's transaction to happen first, right? And imagine you had millions of users and they're all having their own chain. You could potentially run thousands of consensus at the same time, parallelly, right? And we kind of, if anyone here has really modeled data structure before, you can kind of spot a problem here immediately, is that the whole security of the blockchain relies on the height of the blockchain. Like we've all added chain state on top of each other. The number of confirmations of the blockchain kind of secures the blockchain more and more over time. But here, because every participant has their own chain, you're going to end up with a lot of shallow chains. Not every participant is very active. People only use 4 or 5 transactions a day, maybe max, right? So the amount of transactions on an individual participant is going to be quite shallow. This allows us to obviously make the write very efficient, but it does kind of make the chain a lot more unsecure, right? The way we do that is, the way we can kind of solve for that is, not only do you see there are chains between the blocks of participants, you can also see there are sideways links between participants, right? So you end up creating, so you no longer need to rely on the height of the chain for security, but rather the fact that it's a web, it's a lattice, like sideways transaction links and up and down interactive, like sideways interactive links and up and down transitive links, right? These kind of create this lattice model, and this is what we call, like inside the code, it's called a tesseract lattice, right? This whole data structure, but the way that we manipulate it and manage it is called the multi-link DAG, and this is one of the core innovations we had to do. The next is proof of context, right? Now, looking at like our previous model, like say if Alice and Daisy wanted to have a transaction, how do we go about doing this, right? There is a context, and this context effectively in the context of the consensus model translates to a set of nodes, right? So Alice has a set of nodes and Daisy has a set of nodes who are secure in her chain, right? We call them guardians. And when Alice and Daisy want to make a transaction, these two sets of nodes have to come together, right? And there is an operator who comes in and then kind of orchestrates this whole thing. His job is to kind of put the cluster together, right? He goes to Alice's nodes and says, I have a transaction for Alice, do you want to join my cluster? And he goes to Daisy's nodes and says, join my cluster. And if 2/3 of both these nodes are here, we have a guarantee that Alice's nodes cannot be attached to someone else's consensus, right? So now I have 2/3 of Alice and 2/3 of Daisy, I'll go out and get another 1/3 from the network. Enough so that Alice and Daisy, if they decide to collaborate, cannot game the system. The network entropy will make sure that there is some randomness in the network entropy that effectively translates to, it's all about the selection of these random nodes. That's where the whole game is, right? If you select a network entropy in such a way that this small 100-node cluster is as good as achieving consensus on a 1,000-node network because of the randomness there, then you will effectively manage to make it completely scalable, right? You're achieving BFT on a 100-node cluster, but thousands of these clusters can occur all the time, and all of these clusters individually have the security of the whole network, right? So you manage to retain security, and you also manage to make the network extremely scalable at the same time, right? And the phrase we use here is local finality, global truth, right? These context nodes, these Alice's nodes, these guardians, they are guarantors of Alice's latest state, right? If I wanted to know Abhishek's latest information, right? In the real world, let's not talk about blockchains here. If I want to know something about Abhishek, who am I most likely to get the most accurate information from? His family, his friends, his colleagues, people who know him. Today's blockchains, or even today's content ID-based systems, basically, to know something about Abhishek, who's from India, I have to go to Siberia and go to every house on the street and be like, do you know Abhishek? Do you know Abhishek? Do you know Abhishek? At some point, someone's going to randomly have a chance of saying, I do know Abhishek, I have some information, here's the latest state. But once I have these context nodes, these nodes are guarantors of Abhishek's latest state. I no longer need to randomly look all over the network to find Abhishek's latest information. I just have to look at one of his context nodes. And they are guaranteed to have the latest state because they're part of the consensus. And therefore, they were immediately given the latest information after the transaction on Abhishek, right? The next big one is PISA, the virtual machine. We'll kind of dive into it a lot more when we get into the programming of how to build and program for PISA, but effectively it's one of the possible virtual machine runtimes for MOI. It's a register-based virtual machine, and it allows for safe, stateful execution on both ephemeral and persistent states. It's one of the, obviously the fact that we brought in the idea of ephemeral states means this today is the only virtual machine that can kind of program for both. And the way the execution architecture is built for MOI allows not just PISA to be the core thing. PISA is the one that exists today, but we're already working on the next two virtual machines. It's called Meru and Hanoi. Meru is basically like kind of like the FVM. It's a WASM-based architecture, allows for WASM-based actors to exist in them. And Hanoi is a multi-party compute-based virtual machine, and you can do privacy-safe computation on top of that. yeah, so as of right now, we have our second testnet Babylon live, and you can kind of start programming on it right now. There's a faucet, the testnet is doing quite well. We have about, I think, 650, 700 validators on it right now, and it's growing every day. And we're already in works for our next testnet, and I'll kind of talk about that in a bit. But there is the SDK you can use to start programming on it, and there is MOI Voyage, which is kind of our explorer / faucet. It's kind of like a facilitator for the testnet right now. And if you can also become a guardian, it's a public testnet, so anyone can join and become a guardian and earn rewards right now. We're giving away as much as 200 MOI tokens a day right now. And obviously this will change as the challenge model and all of these get involved over time. But as of right now, just put up a node, you get 200 MOI tokens a day for hosting that node. And these are the kind of interactions we have available today, right? So let me take this chance to kind of introduce the idea of interactions on the protocol, right? Is that we don't do traditional transactions. So if you look at Ethereum, you just have this idea of transaction, right? If you want to create a contract, you would fire it without an address and with some code, and then it would create a new account with the contract code inside it. And if I wanted to transfer, I would not have some code there, I just put some money in there. So the transaction object is kind of a generic envelope for doing anything you want with the network, right? And the network basically expects you to abstract all that down to the smart contract level. What we've decided to do is move that up one level to the user, and if you have a specific interaction you want to do on the network, there is a particular interaction type for that. For example, you want to transfer asset, there is IX asset transfer. Just pop that in, give a sender receiver, specify the asset ID and the amount, boom, it just does the work, right? The envelope for IX asset transfer is very specific. It's not generic. It's not like not all asset interaction objects have the same structure, right? Asset create. This is another really cool interaction. You do not need to fire you don't need to deploy a smart contract for assets, and I'll kind of show you what that looks like. But I can just fire an interaction as easy as firing a transaction, and boom, I have a new asset created. It will be in my wallet, minted, and it's ready to go. I don't need to deploy, I don't need to write solidity code, I don't need to write an ERC20 contract or any kind of contract for that matter, right? And apart from that, today in Babylon, we also have mint and burn for if you created a MAS0, which is equivalent to an ERC20 contract. If you created an asset of the MAS0 variety, you can mint and burn its supply, right? And in the future, we're going to be adding lockups, approvals, revoke, and all that stuff. It doesn't exist today, though. Right? And in terms of logical interactions, we can deploy a logic today and invoke a method on that logic. The endlist method is used for managing logics which are purely ephemeral, right? The same way when you deploy a logic, you have a constructor associated with it. When you deploy an ephemeral logic, you have to have a enlisting method for me to initiate my state with that logic. The logic needs a way to know that I am an active member of this logic, right? And for interactable calls, you need to use IX logic interact. And yes, we do support upgradability. It is the contracts are immutable, but the way the logic object structure is architected is that there is a unique logic ID associated with that address. And if you upgrade the logic, and when we say upgrade, it means extend. You cannot just change all the methods. You can add new methods. You can add new state fields. You cannot remove the ones that already exist. So if you were to extend the capabilities of a contract, you can count that as an upgrade, and you'll be given a new logic ID under the same address for that logic, right? So, and there's a built-in namespace service on the logic. So instead of using the logic ID, if you were to use the logic address, it will automatically route to the latest version of the logic, right? And yeah, so like I said, we have a testnet coming soon, probably in the next month or so, where it allows you to start working with ephemeral states, has atomic storage handling, event emitting, approvals and lockups, native asset handling inside the PSA virtual machine, and bundling interactions, right? All of these are available in the next testnet, and we are planning to have another one after Olmec, before we go mainnet by the end of the year. So yeah, to get started with MOI, you guys can pull up a laptop and give it a shot at the same time if you want to. Just install the MOI.js SDK, and then you're good. You have basically all the tools you need to just start working with the protocol with just interactions. So if you wanted to build an application, you don't really need a programming language. You could write a dApp today without writing a single line of Solidity to manage assets, to send assets across the entire thing. Between participants, you could transfer assets, you could increase and mint, burn, and supply. We have actual dApps today. You can go to MOI.Technology/alpha and find out people have already started building these kind of things, right? And all it takes is a few lines of JavaScript. You don't really need to, and I'll show you what that looks like, right? Does this look visible? I can kind of zoom up if you have to, but basically I can use the IX asset create interaction type And this is JavaScript code using the MOI.JS SDK. All I do is send an interaction of type asset create. You can see that. Fuel price is 1, that's the testnet fuel price. The fuel limit is whatever you want to specify, 200. It costs about 100 to create an interaction asset today. And the payload says standard, and you see the standard says 1 today. And as of now, we just have 2 standards we built for the testnet, but this is a very extensible format. So we could have MAS 3, 4, whatever, like we could have a whole bunch of these to support SDTs and all different kinds of assets. But as of now, we have support for ERC20 contracts, ERC20 tokens called MAS 0, and ERC721 for NFTs on MAS 1. So if you want to create an MAS 1, which is in this case an NFT, Candyland 001, supply can only be 1. And all it takes is to fire this interaction and you will have an asset created. You don't need to write Solidity code or submit an contract into the network for this token to be registered. As soon as you fire this interaction on the sender's balance, there will be an asset ID for Candyland with the amount equals 1. Right? And this is something you can do today. This is like actually available on the Babylon testnet right now. You can create MAS 0 and MAS 1 assets right now, and we're working on adding more standards in Olmec. Right? The next one is deploying logics, right? Again, I'll show you what the manifest and what it takes to actually go ahead and write a contract and deploy it. But again, this is again very simple. You just create a factory and then you just deploy on that factory with the constructor, and boom, you have it. And this is the IX logic deploy, and I'll show you what the manifest structure looks like. I have some things to blow your mind there, but let's see how that goes. So this lets me segue into the programming language we had to write to make all this possible. It's called Coco. And you can kind of check it out today. You can download it. It's in public alpha. You can just head to cocolang.dev, have it set up. We support all the operating systems and architectures today. And you can get started right now. And it gives you quite a lot of capabilities to compile into the protocol as it stands. But what is Coco and why did we need it? And let's kind of break that down. Before I show you like a snippet, like the idea with Coco was always that we needed a language that prioritized readability and auditability, which in my opinion is the most important part of building contracts on Web3, right? Because what is the point of giving developers a lot of capabilities if someone cannot verify that this is not breaking state? Like, if you're going to build real enterprise use cases and real world use cases for blockchain, you're going to need a blockchain that is very easy to prove and verify that it does exactly what it says. In my opinion today, Solidity or Rust for that matter don't offer this degree of readability or auditability for that matter, right? If I'm going to expect end users to kind of validate the code that they're interacting with, which is the whole promise of blockchain, right? The guarantee that end users can know what they're working with. The code that they're reading, they should be, if they're programmers, they should be able to read the code and in a second understand that, you know what, I'm not getting screwed up here. Like the logic is safe, everything I'm seeing looks good. I'm going to rely on actual auditors and certifications, but at the very least, I have a first glance advantage of knowing that, you know what, this just kind of works, right? Coco today can compile for the PISA virtual machine runtime, and in the future is also going to be supporting WASM and other, and can even compile to EVM in the future. But yeah, as it stands today. So let's just take an example of a simple flipper. You guys have all probably seen this contract when you're learning Solidity for the first time, right? It's a very simple flipper contract. It just has a single Boolean value and a couple of methods to flip it, set it, get it, so on, right? And if you compile this today with Solc, this exact contract, you will end up with 443 opcodes and 633 bytes, right? There's a lot of data on its own, but and if you wanted to interact with this contract, you would have to expect the app developer to provide the ABI to talk to that contract, and you'd have to store that as part of your application, right? This is a potential attack vector because you have to trust the ABI. The ABI can always talk to a different contract than what you expect. You have to trust the application developer to give you the right ABI. It is possible. It is a real attack vector here for people to kind of spoof people into talking to the incorrect contracts, right? If you were to write the same contract in MOI with Coco, this is what the contract will look like. It's more or less the same size, and I'll break down the lines of the code, but it would give you just 18 opcodes, and that 471 bytes includes the ABI, and it's on-chain. You do not need to keep an ABI with you when you're writing applications. You can always pull it from on-chain and make sure it's verified, because the contract address you want to talk to has the full ABI associated with it on-chain, right? And including the ABI, it's only 471 bytes. The reason we can do 18 opcodes for the first part is because PISA is a register-based opcode, not a register-based virtual machine, not stack-based. It takes, on average, a lot fewer opcodes to make something happen on a register-based virtual machine than a stack-based virtual machine, right? So a simple operation, as simple as reading input value to the function, can take as many as 20 opcodes on the EVM, just one on PISA, right? So I'll kind of show you what the manifest looks like when we start developing on Coco. And yeah, like I said, you can kind of get started with Coco today. You can head to cocolang.dev, get it installed, and you can code along if you're interested. There's also a VS Code extension you want for syntax highlighting and basic error handling that you can get on VS Code. Just type in cocolang and you should be able to get the extension. And I'll kind of show you what the live coding looks like in a second. But before that, anybody have any questions? Okay. Okay, so I am in VS Code. I have the Flipper contract we saw earlier. Let me just, yeah, I gotcha. Okay, so I have the simple flipper.coco module here. So to get started, usually what you need to do, if I were to, like, let me just do this for the sake of the crowd. Let me add a new window here. Alright, so to get started with the Coco project, the first thing you need is a coco.nut file, right? A coconut file is basically like a package or JSON or a go.mod, whatever programming language you're used to. It's like a file that helps you kind of index dependencies, gives you a sense of what target you want to compile for and all that. So you just kind of get started with, I think you just do coco mod init. Oh, my bad. My Go programmer and me kind of took over for a bit. Coconut init, let's just call this Flipper. And if you do this, you should see a coconut file there. And it has the basics you need, like the version of the Coco compiler you're using, the name of the module, the version of the code you're using, the license repository, you can fill all this in. And the important ones here are the target and the architecture that you're compiling for. I'll just go back to my actually ready module here. But yeah, if I go here, you can see I'm compiling for the MOI PISA architecture right now. You can, as of, it's not available in the current release yet, but in the upcoming release, you can also compile for native PISA, which is basically a version of PISA that does not run inside the blockchain. It's just a empty virtual machine that can execute on its own. And when you compile the manifest, you can also ask what format you want the manifest in. You want a JSON format for the SDK to be able to work with it, but you can also generate a raw bytecode version or YAML version, whichever you like. And the way you generate the instructions, you have variety there also. You can compile it in pure binary. You can ask it in hexadecimal or in assembly. In general, binary is going to be the cheapest to compile. Hexadecimal is all right. Assembly is going to be the most expensive to compile, but it's great for reading. It's great for debugging and stuff. And there are tools available today within the SDK for you to download a manifest for a logic that already exists, and then convert that between different code forms and file forms if you wanted to, right? Now let's look at the contract itself, right? So the first line, of course, just gives you the name of the module, and you can have multiple files in the same directory, indicating that you can just kind of spread them across multiple files. And if you wanted a sub package or something like that, you could have a directory, and that directory, all the files in that directory would have to again maintain the package name, right? Coco does not support packages in its current form, but as of 4.0, I think we're supporting local packages, and by 5.0 we're going to even support external packages you can pull in. Anyway, so the first thing we do here is we declare a persistent state, right? And if I want to declare an ephemeral state that lives on the participant, it would work the same way. All I'd have to do is specify ephemeral and then have a whole structure of values, field of values there, right? But obviously today Coco doesn't support ephemeral programming, so that's coming in the new testnet. But let's say I have a persistent state, this is a Flipper contract, it just has a value, which is a Boolean, simple. And this endpoint deployer. So in Coco, when you're talking about functions which can be called externally, instead of calling them pub-func, you would just use endpoint deployer, which specifies that this is a callable endpoint and it has a deployer nature, right? So there are, as of now, you have two kinds of endpoints, deployers and invocables. And when you wanted to write a constructor for an ephemeral state, you'd use endlister, and for intractable calls, you'd use intractable, right? When those eventually come around, right? So in this case, my constructor does nothing. Coco and the PISA virtual machine support nil value, kind of handling nil values very efficiently. There is no data type called null, but if the value is empty, it will revert to the default value for that data type, right? So in this case, I don't want to deploy any constructing. I don't want to construct the state value, so I'm just passing on the constructor. You do need at least one constructor, but Cocoa also supports multiple constructors. So something like Led Zeppelin contract. So Led Zeppelin can write a whole huge contract where they have multiple constructors, and when you're deploying that, you can use the one that you want, right? With whatever suits your purpose. So this is a commonly requested feature in Solidity for people to have multiple constructors, and this is actually possible with Cocoa. And if let's say I want to read the value from the state, right? So if you notice here, the flipper here corresponds to the module name. It's the logic itself. So you see these ones in orange, they're basically in PISA and Cocoa, we call these super globals, right? The idea with them is that there's something like flipper, sender, participants, IXN, which is interaction, and ENV, the environment. These are super globals that exist in all contexts of the programming, so you can kind of take it in any function, any endpoint, in any class. You can use the values from there if you need to. So these super globals kind of are just long-living globals in the execution environment itself. And in this case, if I wanted to read the persistent state value, I'm basically saying on this character called flipper, which is itself an account, right? So flipper.state.value, I have to observe this symbol into a local variable called value. And if you notice, value is also the output symbol, so it will just kind of read into the output symbol and get returned, right? And if let's take a look at this set function, right? If I had a value and I want to set it, I would use the mutate keyword instead. And you notice the arrow is the other way around. I'm moving this local variable value into the symbol, which just overrides whatever values in that symbol. And this will only work for scalar types. You can't do this on collections. On collections, you would have to kind of capture them in this way. So if you see in line 36 and 37, if you see the mutate arrow is the other way around here. So I'm capturing the value from flipper.state.value into the local variable called value, and then I'm just negating it. And when I do this negation, whatever the final value of this variable called value is at the end of this context, it will just revert back to flipper.state.value. Right? This way, it's kind of a Rust-like mechanism where you kind of have to borrow the state symbol, and you have it available in the local variable in that intended context. And at the end of the intended context, it just reverts back to flipper.state.value. Right? And you notice that the last function here, the set function here, it's the function, not an endpoint. So functions in Cocoa are not externally callable. They can only be used internally. They're kind of like for modelizing code and just for efficient programming and stuff. But if you want to make a function externally callable, you have to use the endpoint structure. But yeah, that's kind of just, and if you go ahead and let's go and compile this, right? So all it takes to compile this is you do Cocoa compile. It looks for the coconut file and uses the information available in that. You can override that with your own CLI arguments, but it will default to whatever is there in the coconut file. And if you did this, it is right now just generated a flipper.json file. This is a more difficult version of it to read. This is the ideal format for deploying with the SDK, but let's just say I wanted a more easy version to kind of read, right? This doesn't make sense. Let's see enough. Let's say I wanted to go YAML because I like YAML more, just for the sake of it. What is going on? Okay, flipper. And instead of binary, because it's very difficult to parse the opcodes, let's go with ASM because it's just easier to read the opcodes here. And if I did this, you'll see there's a flipper.yaml file here, and this is a little bit easier to kind of go through. It takes this is a readable version of your ABI plus your contract code. It's a single artifact, right? This is the artifact that is available on chain that you deploy with the SDK and everything, and this gets converted into a logic object and stored. And you can always query for the manifest from the protocol to make sure that the ABI is consistent with the logic array that you're working with, right? Here you can see this is the kind of the opcodes we have for the PSA virtual machine, and this is the seed function. Let's take something simple like the get function, right? This is get, and let's just right. So if I take the get function, all I'm supposed to be doing is observing the value and then returning it, right? So pload does persistent load, right? This is loading state from the persistent state. And I'm reading that into a register called $0, and then I'm just yielding that out to the value called value, which is at position 0, right? And if I was trying to set, let's just do toggle, right? This is the flip function. I'm loading the state from the local contract state, and then I'm negating it, and then I'm saving it. That's all it is, right? The opcodes are so light, so efficient. I mean, sure, this is not for everyone to kind of dissect and break down, but the average developer is going to be able to kind of verify and kind of understand what exactly is happening on the virtual machine, right? In the EVM, you need to be a wizard to kind of figure out what the hell is going on from opcode to opcode, right? It's quite complicated, if I'm being honest. But yeah, the nature of the opcode is much lighter, very easy to kind of dissect for average developer and know what's happening inside the virtual machine, right? Now, once you have this manifest, right? So you need a way to test it. So today we don't have something like, and I saw the guys from Stella showing Okashi, that looks great, and we're kind of working on something similar right now. As it stands today, you can only do this using a CLI, and it's called Logic Lab. It comes alongside the Cocoa binary today, and tomorrow is actually going to be part of the Cocoa binary itself. You would not need a separate binary for this. You could just do Cocoa Lab in it. But if you wanted to do this, Logic Lab comes with Cocoa Lang. So when you install Cocoa Lang, it comes ready to go. So you just do Logic Lab init to kind of initialize the Logic Lab environment. It initializes locally in this .Logic Lab environment. And once you have the environment ready, we can start the REPL. You just do Logic Lab, start, and boom, you're in the REPL. And this REPL just gives you something it's like a very similar environment for you to just play and experiment with the logic. You can just run users here to see there are no users in the environment and there are no logics on the environment right now. And if you need any help with this, the documentation is on the Cocoa website, but you can also just do help and it gives you some basic information. Any of these colored texts are help strings themselves. So if you wanted help with the register command, you just run help register. It'll give you a basic example and some usage, some basic how to documentation. Now let's say I need to do an interaction on this logic, right? First thing I need to do to deploy the logic is I need a participant to do that. I need a sender, right? So you go ahead and just do register Manish, and this will create a user with the address that you just see there. And you can verify this again by calling users, and you can see Manish has that address, right? Again, this is all running locally. It does not require even a local blockchain node. It's just running PISA in a local form, right? And once I have users, now I got to go deploy the logic, right? So just to refresh my memory, I can go and do help deploy. Deploy there, and you can see to deploy the logic, I would need to specify exactly how I want to deploy. So the name of the logic, the call site, and the arguments for that. So in our case, before we deploy, I need to first create the logic. So I need to take the manifest and I need to add that into the environment. And the way you do that is compile, and let's give it a name, Flipper, right? Flipper is a name from, you can specify manifest, and in the future you can also specify from Cocoa, and it'll compile the Cocoa source file into the manifest and then take it directly into the environment. But in this case, I'm giving a already compiled manifest, so it'll be flipper.json. It is in Logic Lab, you can use any format, everything will work. So you compile this Flipper, it costs about 350 fuel right now, and this is the new logic ID for that logic. And you can see more about that by doing get logics.flipper, and it will give you some basic information about the logic. So there's a logic called Flipper. It's currently not ready because it's a logic with a persistent state that's not been deployed yet. You've just created the logic object. It's not been deployed yet, so it's not ready to interact with. There's an address for this logic, there's a logic ID, and the edition is currently 0. If you were to upgrade it, it will become edition 1. What engine is running on, what is the hash of the manifest, does it have a persistent state, true, ephemeral state, false, does it have interactable calls, false, and is it an asset logic, false. So it just gives you some basic metadata about the logic, and here are the call sites we have, right? So we have the init, which is the deployer, the get, the toggle, the seed, and the set methods. Whatever we saw in the contract, all you can kind of inspect all that here. And let's say you wanted to deploy just to make this logic ready. You can see now that the logic is marked as ready equals false because it's not been deployed yet. So you can go ahead and let's say I do deploy flipper dot, I'm using the method init to do this. Init does not take any input, so I can just call this no designated sender. Okay. So the problem is I have created a sender called Manish, but I have to mark him as the sender for the interaction I'm sending. So you do this by just doing set designated. I gotta remember this command, help designated. And to set the receiver, I just do get designated.sender and then send. Okay, so I can just do get designated.sender, and the user we create is Manish. So Manish is currently designated sender. And now that I have Manish, I can now call deploy on this. What's going on? Give me a second, guys. So users, we have this person. Oh, my bad. I gotta use set. Right? Manish is now set as the designated sender, and now when I call deploy, Manish will be user sender. It costs something. Since we didn't execute anything, zero fuel here. So now when I go and do get on the Flipper, you can see that for Flipper now it says ready true. So now you can start making calls on it, right? So you can now start toggling its state and everything. So let's start with something simple. So I'm going to invoke flipper.get. Right? and you can see the current value is false on that contract. So now if I were to go and toggle it, it should flip, right? So we'll go and toggle. Toggle is a stateful call, so we have a bang there to indicate that it's a stateful call. You do that, cost 170, and the state got toggled. And you can verify this by calling get again, and you can see it's true, right? This just gives you a very basic CLI to kind of just help you kind of play around with the logic and make sure everything is functional and working before you actually deploy that to chain. We are working on a version of this that works with an API. It will have a physical UI UX model within Voyage, so what you saw you can do with Okashi, you could kind of be able to do with Logic Lab as well. It looks very similar. But yeah, this is the basic kind of Logic Lab. So once you have it ready, you can use the JS SDK like I showed you to deploy this. Where did that go? Right there. So you would use a code like this where you would read the manifest from the JSON file into this factory, and then you just call deploy with the call that you want. What is the values, the fuel price, fuel limit, so on. Boom, logic deploy. That's all it takes. But yeah, that is a brief introduction to MOI. Excuse me. Hope you guys found this useful. Yeah.
I've got a quick question. So you talked about assigning assets and adding the logic to that.
Yeah.
Is that something you can quickly just explain what the steps are in that?
So can you go again, like create an asset
Create
and
an
then
asset and then assign the logic to that asset.
Alright,
That's when you can quickly walk through what the steps would be?
Yeah, so this is a property that I actually kind of glanced over, thanks for catching that, is like, if you wanted to have an asset that did not comply with the MAS0, MAS1 standard, you wanted to write your own custom logic, custom standard, whatever, there will be an asset standard to support that, and you could write a Coco code that kind of handles all the logic required for the transfer logics, sender logic, all the basic handling for the asset, and then deploy that alongside the asset. And whenever you try to transfer that asset, it would make a contract call to kind of facilitate and make sure the transfer logic is there. But the actual movement of assets is still happening at the native protocol layer, right? And you would not need, what do you call that? You would not need to rely on the contract being safe. All the contract is doing is verifying that the conditions for the transfer have been met, and then facilitates the transfer through the protocol layer itself. All right, so yeah, sorry. So it looks like we bounties and grants, we have some of these as well. So as part of ETHDenver, again, we have about a $300 bounty if you wanted to go ahead and build something on MOI today, and anything. So you can take a look at MOI.Technology.com/alpha. Alpha projects. So MOI.Technology/alpha projects, and you should see some of the things that others have built. You can head over to Server Labs' GitHub and see some examples we have. Examples for Coco, the JS SDK, it's all out there. The docs are kind of still getting improved, but then you have there's quite a lot there right now, and we are here for the next week. So if you have any questions, feel free to reach out, and then we can do something. Like, happy hacking, guys. Have a good one.